Okay, so I'm Eleanor. I'm second year environmental science. I'll be talking a bit about remote sensing data to model sea ice retreat. And again, can't see the chat, so I'll take some questions at the end unless Claire can speak about it. So I'm sure you can all recite all of the goals by this point, but just in case, here are the ones this talk covers. So it's 13 of climate action, 14 of life below water, and 15, which is life on land. So what is remote sensing data? In terms of definitions, remote sensing data is the acquiring of data from a distance. So for example, ships can do this by using sonar, where they find out ocean depth without actually having to dive down there. And images from satellites can be taken of Earth to find things we can't see from the ground. These images can take photos of things like forest fire, land use changes, or of ice melt. So NASA uploads all of these satellite images to a website called Worldview. In order to get these images, I wrote a code to download them because manually clicking to get every image that exists would have taken an age. After that code's complete, and that can take even a few days to run constantly, I wrote a code to project them. And to do this, I used a Python package called CartoPy, which is basically Python's go-to package for mapping. And then I projected them onto a globe with a focus on the Arctic. This is just an example of part of one of the scripts I wrote to show the images. So when writing the code to project them, you need to decide on what the projection is. So this determines how the world's viewed. You can view the whole world from different angles, or you can just focus on the Arctic, which is ideal for this scenario. This just means that you can see the right trends. Like you're not exactly going to be able to monitor Arctic sea ice retreat from a projection of Spain, say. So I'm not going to show my overall time lapse, as you'll probably get quite bored after a few minutes, but here's an example of just 2002, which is the year the newest imaging satellite was launched. Hopefully this works. So you're probably noticing the big black hole appearing, and that's polar night, where nighttime lasts for over 100 days at a time. And obviously that's an issue when it comes to observing trends outside of summertime, but other imaging layers like brightness temperature can be used to see what's underneath. So this is an example of brightness temperature I mentioned. It's just an example of December 2020, and here we go. As you can see, there are colours instead of that black hole. There's a small one, but that's just because of the orbit of the satellite. This uses the Advanced Microwave Scanning Radiometer Earth Observing System, or for less of a mouthful, it's called AMSA-E. It just shows brightness temperature, so the more blue there is, the more sea ice there is, basically. Why is this useful? So this kind of data processing is really important when it comes to presenting research. It's quite hard to determine the extent of sea ice retreat just from raw data, so we need these kinds of visual aids to show it and just make it more exciting, really. So one example of how this can be useful is the 2012 sea ice low. Arctic ice does go through a cycle of expanding and melting through the seasons, so it's not terrifying news to see it shrink in the summer, but 2012 was particularly bad news. That year was 50% smaller than the long-term average and 18% smaller than the previous record low, which was in 2007. There are a few areas this could be seen pretty clearly, like the Fram Strait, which is the east coast of Greenland. I'm not sure if you can see my mouse. But you can see a lot more white on that east coast of Fram Strait in the 2012 one. Well, you can see more white in the 2021 than 2012. This just shows how extreme the low was, considering 2020 is 8 years ahead, so we'd expect a lot less sea ice if it followed the 2012 trajectory. However, we would still expect the Arctic to be ice-free in summers by 2050. So I thought I'd end on a bit of a cheerier note. So see if you can have a guess what day this is, any day between 2000 and present day. I've put on brightness temperature as well. because the polar night might give you a hint if you were paying attention earlier. I think I'll be able to check the chat on my phone, so just put things in there if you can.
I'll check the chat, Eleanor, for you.
Thank you. No bad guesses here.
Do we get any clues, Eleanor?
Absolutely none. Could be any day.
So no guesses yet.
Date range is any day between 2000 and present day. Winner gets no prize. Yeah, Ashley, that is exactly right. One guess. It's not too far off in the grand scheme of things. Give it a few minutes. Well, a minute. Any year, Laura? Okay, I'll put you out of your misery. So that is the 3rd of January 2003, which also happens to be the day Greta Thunberg was born. So let me know if you have any questions.
Thank you, Eleanor. So that is an interesting coincidence, isn't it? And it was absolutely fascinating seeing those visualizations play out. As you made the point, it's a really effective way, really helpful for presentations, to show, show the impacts in a very clear way, and great to also then take snapshots of different dates, different years, make those comparisons, and see how things compare. So thank you very much for that, Eleanor. As ever, please, everyone, add your comments or questions into the chat. And I think also at this point, we have a few minutes before we close the session at 12. So if you have any further questions related to any of the speakers' presentations this morning, please do add them. I know there was a question that just came in just slightly after Ejiro's presentation. I think that's been covered on the chat, so thank you, Aratrika, for that. But if it hasn't, or if there's any follow-up questions on that or anything else, please let us know. So we'll just give it a minute or two for questions.
Not a question, but if anyone's on campus, head on down to Parkinson Court because we have a lot of free food there.
Thanks, Eleanor. Yeah, you've stolen my thunder with the next part, but yeah, absolutely, we'll be completely promoting that. Absolutely. Yeah, lunchtime is coming shortly, and yeah, there's, as well as the great presentations, the posters, the art exhibits, there is some soup, so and refreshments, so please head on down there if you're in Leeds or on campus at the moment. So I think just to check the chat, Kate asks, Eleanor, since you completed your work, where has it been used?
Great question. I actually have no idea because it's been used by the Centre for Polar Observation and Modelling, and they go to conferences like, I don't even remember what it was called now. The massive one in Edinburgh. I'm having a brain freeze. Anyway, that the
COP.
EU COP, that's the one.
COP 26.
And how long did it take to write the code initially? I'd say about 2 weeks, to be honest, because there's an absolute ton of trial and error with Python type stuff. It's practically fluke at the first try, if it works.
Will that code form the basis of, will it now kind of set the path for future coding and work? Will it make it easier going forwards?
Yeah, massively. It's super useful. You could just download it and send it to anyone.
Okay.
And they can do exactly what I did.
Wonderful. It's really, really exciting. And a few further thoughts and comments. Laura asks, what else have you written code for?
Practically half the stuff I do on my course. Like I do a lot of data analysis with it. So I did some work on the Montreal protocol that took halocarbon data, and I extrapolated that data to see if it fit the projections that were set out by the protocol. Unsurprisingly, they don't fit the projections, they're way above them, but it's really useful for visualizing that kind of thing.
Yeah, absolutely. And we have another question from Vanessa, and she asks, are you using a specific software for writing your code? This is very interesting.
Thank you, Vanessa. I'm using Jupyter Notebook, which is just through Python, so you can access it anywhere. It's really useful.